Hello everyone, my name is Shweta Soumyajla. Today I am talking about dangers of data replication and a solution. These are the contents I am focusing today. That what is data replication, problems of replication, challenges to solve the replication, replication models, validation and conclusion. So, what is data replication? Data replication is the process of storing the same data in multiple locations. Data is replicated at multiple network nodes for performance and availability. This is often done for data backup, disaster recovery, or to improve data availability and performance. These are the problems of replication. The first one is data inconsistency. If data is replicated incorrectly or incompletely, inconsistencies can arise between the original and replicated data. This can lead to data corruption and can make it difficult to maintain data accuracy and integrity. The second one is replication latency. Depending on the replication method used, there may be a delay between when data is updated in the original location and when it is replicated to the secondary location. This can result in inconsistent data between the two locations, which can cause issues for applications that rely on up-to-date data. The third one is storage space. Replicating data requires additional storage space, which can become a significant issue when dealing with large amount of data. This can be especially problematic if the replication is being done across multiple locations, each of which requires additional storage. The last one is network bandwidth and latency. Replicating data can consume a significant amount of network bandwidth, particularly if large amount of data need to be replicated. This can cause network congestion and can lead to slow performance for both replication and other applications. Now, the challenges which are faced to solve the problems are: the first, mobile nodes disconnection is the major problem faced in the replication the data from one node to another node. The second one is update anywhere, anytime, anyway transactional replication has unstable behavior as the workload scales up. A 10-fold increase in nodes and traffic gives a 1,000-fold increase in deadlocks or reconciliations. Now, let's take a look at the replication models. There are 5 replication models are explained in this paper. First one is eager replication, lazy group replication, lazy master replication, non-transactional replication scheme, and two-tier replication. So, what is eager replication? Eager replication keeps all replicas exactly synchronized at all nodes by updating all the replicas as part of one atomic transaction. There are no serializations, that means there are no inconsistencies and no need for reconciliation in eager systems. Locking detects potential anomalies and converts them to waits or deadlocks. With eager replication, reads at connected nodes give current data and reads at disconnected nodes may give stale or out of date data. Even if all the nodes are connected all the time, updates may fail due to deadlocks that prevent serialization errors. The following are the formulae that represents the eager work rate, transaction size, transaction duration, and total TPS. The action rate is measured by total transaction per second multiplied by number of updates in transaction multiplied by number of nodes. Transaction size is measured by number of updates in transaction multiplied by number of nodes. Transaction duration is the multiplication of number of updates in transaction, number of nodes, and time to perform an action. And the last one, the total transaction per second, is measured by multiplication of total performance per second and number of nodes. It is surprising that the action rate and the number of active transactions in the same for eager and lazy systems. Eager systems have fewer longer transactions. Lazy systems have more and shorter transactions. The problems of eager replication. The problems of eager replications are mobile nodes cannot use an eager scheme when disconnected. The second one is the probability of deadlocks and consequently failed transaction rises very quickly with transaction size and with the number of nodes. A 10-fold increase in nodes give a 1,000-fold increase in failed transactions. Now the second model is lazy group replication. Lazy group replication allows any node to update any local data. When the transaction commits, a transaction is sent to every other node to apply the root transaction updates to the replicas at the destination node. Timestamps are commonly used to detect and reconcile lazy group transactional updates. Each object carries the timestamp of its most recent update. Each replica update carries the new value and tagged with the old object timestamp. Each node detects incoming replica updates that would overwrite earlier committed updates. The node tests if the local replica's timestamp and the up-to-date old timestamps are equal. If so, the update is safe. Now, this figure shows a lazy transaction has a root execution that updates either master or local copies of data. Then subsequent transaction update replicas at remote nodes. One lazy transaction per remote replica node. The lazy updates carry timestamp of each original object. If the local object timestamp does not match, the update may be dangerous and some form of reconciliation is needed. The problem of lazy group replications are the reconciliation rate rises by a factor of 1,000 when the system scales up by a factor of 10, and two transactions at any two different nodes may update the same data during the disconnection period. Now, the third model, lazy master replication. Master replication assigns an owner to each object. The owner stores the object's correct current value. Updates are first done by owner and then propagated to other replicas. Different objects may have different owners. To simplify the analysis, we assume that node originating the transaction broadcast the replica updates to all the slave replicas after the master transaction commits. The originating node sends one slave transaction to each slave node. Slave updates are timestamped to assure that all the replicas converge to the same final state. Problems of lazy master replicas are: lazy master replicas required contact with object masters and so is not usable by mobile applications. Lazy master replication is slightly less deadlock prone than eager group replication, primarily because the transactions have shorter durations. Non-transactional replication is a type of data replication scheme in which updates are not propagated in the form of transactions. In this scheme, updates are applied to the replicas immediately as they occur on the source database without waiting for a transaction to be completed. Non-transactional replication is typically used in systems where performance and scalability are critical and where the consistency of the replicated data is less important than the speed of replication. While non-transactional replications can be faster and more scalable than transactional replications, it can also result in data inconsistencies and errors. This is because updates may be applied to the replicas in a different order than they occurred on the source database, leading to data inconsistencies between replicas. And the example of non-transactional replications is Microsoft Access. Microsoft has a single design master node that controls all schemes updates to a replicated database. It offers update anywhere for record instance. Each node keeps a version vector with each replicated record. These version vectors are exchanged on demand periodically. The most recent update wins each pairwise exchange. Rejected updates are reported. Problems of non-transactional replications. Non-transactional replications are more prone to data inconsistencies and errors. Now, the two-tier replication scheme begins by assuming there are two kinds of nodes. The first one is mobile nodes and the second is base node. Mobile nodes are disconnected much of the time. They store a replica of database and may originate tentative transactions. A mobile node may be the master of some data items. And on the other hand, base nodes are always connected. They store a replica of the database. Most items are mastered at base nodes. And replicated data items have two versions at mobile nodes. The first is master version and the second is tentative version. In master's version, the most recent value received from the object master. The version at the object master is the master version, but disconnected or lazy replica nodes may have older versions. But in tentative version, the local object may be updated by tentative transactions. The most recent value due to local updates is maintained as tentative value. Similarly, there are two kinds of transactions. One is called base transaction and other is called tentative transaction. Base transactions work only on master data and they produce new master data. They involve at most one connected mobile node and may involve several base nodes. But in tentative transaction, work on local tentative data. They produce new tentative versions. They also produce a base transaction to be run at the later time on the base nodes. The figure shows mechanism of two-tier replication scheme. The two-tier replication scheme, base nodes store replicas of the database. Each object is mastered at some node. Mobile nodes store a replica of the database but are usually disconnected. Mobile nodes accumulate tentative transaction that runs against the tentative data stored at the node. Tentative transactions are reprocessed at base transaction when the mobile nodes reconnects to the base. Tentative transaction may fail when reprocessed. Advantages of two-tier replications are mobile nodes may take tentative database updates. If all the transactions commute, there are no reconciliations. Base transactions execute with single copy serializability, so the master base system state is the result of serialization execution. A transaction becomes durable when the base transaction completes. Replicas at all the connected nodes converge to the base system state. Now the validation is problem of two-tier replication model is not explained. And non-transactional replication schemes, transaction time is not mentioned. The last one is lazy master replication architecture is missing, and no real-time applications are described in this paper. Now the conclusion is, data replication over numerous nodes with open access to update is challenging. A two-tier replication method paired with semantic tricks appears to be the answer. Two-tier replication combines the advantages of local update system and an eager master replication scheme while supporting mobile nodes. Thank you.